there is some specifics on how we describe compounds in coordination chemistry. That's what we'll look today. Please read your chapter 19.2. First, coordination numbers in geometry of compounds of 3D transition metals. Number of atoms or groups around central atom we name coordination numbers. We name ligands the atoms or molecule that surround central atoms. So how many atoms you can put around transition metal compound? There are several examples when there are only two of them. Much more commonly, you have four. Four can be arranged usually in tetrahedral fashion, and sometimes, but relatively seldom, in square planar. There is also coordination number 6, that is octahedral. You will never see coordination numbers above 6 in this class, even so they exist. So tetrahedral, as a reminder, has 109 and 1/2 degree between each of atoms in a complex compound. Well, that could be approximation. Tetrahedral environment can be distorted. In square planar, all atoms are in one plane and angles are approximately 90 degrees. Again, some distortions are possible. Coordination number 5 exists. So you have option of trigonal bipyramid or pyramid with 4 atoms in one plane and one above. That's relatively exotic configuration. The most common is octahedral. And now we should consider some possible isomers. Isomer again means the compound has exactly the same composition, but atoms are arranged in different fashion. So this is an example of linkage or coordination isomers. NO2 group is attached by oxygen atom in this example and by nitrogen atom in these examples. Both examples are known. Both compounds are isolated. Another example of geometry isomers is cis-trans. Trans ligands are at opposite sides of central atom. Kind of recall transatlantic, transcontinental. Cis are at the same side. So this is how it can be arranged in square planar, and this is how they can be arranged in octahedral. Trans and cis. Tetrahedral does not have opposite sides, so it doesn't have cis-trans isomer. There is one more case of isomery, that's meridional. 3 atoms are in one plane that includes central atom, like here, and another is here. And facial. three identical ligands occupy one face of octahedron. 1, 2, 3 here, 1, 2, 3 here. We never say meridional and facial, we say mer and pats. Now, naming of complex compounds. We name the ligands first, followed by the central atom. We name the ligands alphabetically. If coordination compound is ionic, name the cation first and the anion second, in accordance with usual names. For neutral ligands, the name of the molecule is used. Four common exceptions are aqua for water, amine for ammonia, carbonyl for carbon monoxide, and nitrosyl for nitrogen oxide. Well, carbonyl and nitrosyl is relatively seldom used, but aqua and amine are fantastically common. Negative ligands, that's anions, the name formed by adding O to the name of the group. So you have chloride, it will be chlorido. Again, formal international, so-called International Union Pure and Applied Chemistry nomenclature reads that names of anionic ligands, inorganic or organic, are modified by O. If anion ends of ID, IT, or AT, final E is replaced by O, giving IDO, ITO, and ATO respectively. Again, you have chloride, chlorido, cyanide, cyanido, hydride, hydrido, acetate, acetato. Oxidation number of central atom in coordination entity may be indicated by a Roman numeral appended in parentheses to the central atom name, including the ending ATE if applicable, but only if oxidation state can be defined without ambiguity. If you do not know, you do not write. When necessary, negative sign is placed before numeral. If oxidation number is 0, you write in Arabic 0. Romans didn't have 0. So let's look at examples. K4, FeCN6, potassium as usual. Hexacyanide ferrate 2. Oxidation number here is 2, so it's specified. Or, alternatively, potassium hexacyanide ferrate 4 minus, which is charge of this anion. Or, you can altogether skip oxidation number and say tetra potassium, 4 potassiums, hexacyanide ferrate. All three are correct. Here you have 6 NH3 groups around 1 cobalt, hexaamine cobalt, 3 for oxidation number, chloride. Alternatively, hexaamine cobalt, trichloride. Here you have 1 chloride attached to cobalt, so it's pentamine chloride, cobalt 2 plus chloride. So we are saying the oxidation, not oxidation number, but charge over this complex. You can say pentamino chloride cobalt dichloride, or say pentamine chloride cobalt and write 3 for oxidation number in Roman numerals. Here you have potassium, tetra, 4, chlorido, palladate, palladium. Oxidation number of palladium is 2. If you have simple ligands like ammonia or chloride, you usually write prefixes di, tri, and you do not need any enclosure mark. But some ligands are themselves relatively complex compounds. In this case, we use prefixes bis, tris, tetrachis, hexachis, and complex ligand names are enclosed in enclosing marks. When we are using diamine for NH3, but bis methylamine for this group, so will not mix with dimethylamine. Example, cobalt, ethandiamine here, triplicate, tris, ethane, 1,2-diamine, cobalt, oxidation number 3, trichloride. Again, it's never a mistake to add tri. Tri can be actually skipped. Here, tetra, aqua, dichlorido, chromium, 3, chloride. Now, your textbook uses the old nomenclature, in which ID, AT were omitted in the names of complexes. It's still in use. It's described in your textbooks. I will accept it. It's not a mistake. It's just old-fashioned.